Good morning, good afternoon, good evening. Thanks for inviting me to this workshop. I will give you an EDA perspective on chips transforming into 3D systems. As we heard already from the previous presenter, going from Moore's law into a more advanced nodes is not always the best technical and economical path forward. So costs since 2012 per transistor increased a lot. So going to the advanced nodes, if you don't have applications or devices which you sell hundreds, thousands or millions pieces, you wouldn't get the NRE cost back. In addition, if you go to more and more bigger chips, the yield is a problem. So even started in 2011, NVIDIA disaggregated a larger FPGA into 4 smaller chips to get a better yield and performance. Another motivation to go to heterogeneous integration is the memory bandwidth. We also heard the more closer the memory is to the processor, the better. So if you need more memory, putting it on a PCB may be not the best option. So you need to be closer, either HBM memories on a silicon interposer or even in a stack configuration. There are more and more chips reaching the reticle limit, so you can't grow an SoC even further. That's a blocking point that people need to think about, having multiple chips in the same package. And as mentioned also previously, is that going to advanced nodes is not always the best for certain applications like analog, or even on the IOs you have, even on advanced node chips, are mostly analog circuitries, which are not best suited for the smaller nodes. And form factor is the last motivation. The functions, the different blocks on a larger chip may be too far away, so it may be better to have them stacked in smaller form factors. Looking at the history, packaging was mostly driven by PCB type technologies, but over time now additional technologies come into the play, like silicon interposers, interconnect bridges, wafer level, high density RDL type packages, and even stacking of chips on wafer or wafer on wafer. So you can imagine from an EDA point of view, there is no super tool that can design all these technologies. Depending on the technology, it's maybe more an IC type tool that is better suited to design maybe a silicon interposer, and other technologies like RDL type interposers may be better suited to work with a PCB type EDA or design tool. And since many years now, packaging is not only driven by the OSATs in the world, but also foundries coming up with technologies and going into this advanced packaging market, like TSMC with CoWoS, with Info, RDL type packages, and OSATs come up also with competing technologies the foundries come up with. So looking at this ecosystem, it's quite challenging, and from a designer point of view, quite challenging to work and design such complex systems. And depending on the technology, again, it's either a PCB type flow, or moving more to the right, it's more an IC type sign-off and methodology flow. So the challenges we see in the packaging or the chiplets and advanced packaging ecosystem is that, different to the IC development, where you select a foundry and a node and you get a process design kit, this ecosystem is not yet there in this market. So it's really challenging for customers to create a kind of assembly design kit, a kind of PDK. So the foundry technologies now help to come up with this ecosystem, which the OSATs weren't eager to provide. So means you need to have the technologies, the design rules, the technology files, the libraries, the assembly rules. So this ecosystem needs to be available to the customer to be able to design these system on package or chiplet-based designs. Another challenge is what also was mentioned in the previous talk is that there is not yet a big market for chip off the shelf chiplets, so that you can do a shopping of certain building blocks you want to put in your system. There are some initiatives already started to provide these kind of bare silicons on the market. But as mentioned also in the previous talk, there are some standardizations going on about the die-to-die communications and interface IPs like UCIe, bunch of wires, and so on. So to make sure that if you buy a chiplet from vendor A and another one from vendor B, that the interface is compliant and is working at the end. And the other challenge on this market is that there are so many different packaging options. It's hard to really standardize on a single interface or a single interface protocol. Another big challenge is that if you go into the system and chiplet-based heterogeneous integration, that design tool and flow will become very complex. So you're not focusing only on designing a PCB, a package, an IC, an interposer, and stacking things on top of each other. You need to now design the whole system involving many different parties and experience you bring together. And it's not realistic that you have one super engineer who is doing the whole chiplet integration. So the explosion and the number of design tools and required experience, that's a big bottleneck currently customers would need to deal with when starting to design these packages. And also the co-design aspect is very important for these systems, so that you don't throw over the wall one fabric to the other fabric to deal with. So to come up with a real optimized overall system, you need to do a co-design of all the different fabrics and stack pieces in your system. The other challenge is analysis and sign-off. So the current flows are mainly focusing on the individual fabrics. So you optimize your package, you optimize your PCB, you optimize your individual system on chips, silicons you want to put in the system. But overall, you need to analyze the whole system. Means you need to go in the early stage already to do some thermal power analysis, as this is often the concern, stacking things on top of each other. Timing analysis on the whole system, especially system LVS, to make sure that the net list you have through all the fabrics through the system is correct. That's also a big challenge. Electromigration of stacked dies, stress test, warpage is also a big topic in these kind of chiplet and stacked dies. And you can imagine the more you put in your system, the higher the capacity of the analysis and the design tools need to be. And finally, you need compliance kits for the die-to-die communication to check that they will communicate according to the standard. And even more complex is the real 3D implementation. So in this case, you design or disaggregate one big RTL netlist into two different fabrics. So you may want to do floor planning, moving the functions or the blocks from in Z direction from the top die to the bottom die. The die may be on different nodes. So these are design challenges, and also from an EDA perspective, a challenge to provide tools and flows to provide a seamless environment to do these explorations, feasibility studies, and finally, send different net lists and implementation tasks to the individual SoC designers. And if you look at advanced packaging with these RDL type interposers, the design flows are slightly different compared to PCB type flows. In this case, it's more an IC type sign-off method where you need to do LVS on the GDS data, do system level LVS, and you deal with thousands, hundreds of thousands of pins and signals in the system. So capacity is again a challenge for the EDA tools. So looking at these advanced packages and chiplet-based packages is, in the past, packaging was treated as a necessarily evil. You need to protect your silicon against the environment. You need to provide a good connection from the silicon to the outside world and redistribute the I/O pitch to have it better suited for PCB design. Now, with this heterogeneous integration and chiplet designs, you can really add value. So you can build real system, you can have an advantage with applications with a smaller form factor and provide real value with the application to your customers. As Cadence, we collaborate. We have a foundry team who collaborates with the major foundries to actually work and enable this infrastructure, this ecosystem for seamless starting of these package designs. Like we are working with TSMC on a standard. They came up with TSMC blocks where you can seamlessly import a design configuration. You get everything, the stack up, the building of your system is predefined. So with this ecosystem, we try to enable customers to get started very quickly without having to ask each individual manufacturer and party to get input regarding technology and getting started with. Looking at the tools and flows we have at Cadence is we are the vendor providing both chip design tools, package and board design tools. So we are unique and we are able to actually integrate all these different tools seamlessly to provide tools, not only tools, but also solutions and flows to address these design challenges. So on the front end side, it's a product called Integrity System Planner that would allow you to seamlessly build up your system with the dies, interposers. It's an open interface. You can import LevDev or native databases, but you can also start from scratch importing Excel files, text files to have your bump arrangements, or you come up with a floor plan in the tool itself. The implementation tools on the chip side, digital implementation in Innovos, Analog Virtuoso. We have an RF microwave application from AWR and all the Allegro technologies for package and PCB design. And on the bottom line, all the analysis capabilities or a partial list of this. So you can imagine there are a lot of tools required to actually make sure that the design is done properly and in the correct way. So for chiplet design, we have introduced since 2 years ago, we call it not tool, but platform. So it actually provides an integration of all our existing tools, giving them access. So in the cockpit, there is this front-end tool, the Integrity System Planner, that builds up your system. and it will write the system in a common multi-technology database. So the chips can be on different nodes, the interposer on another node. You have package technologies, PCB technology. So it's technology independent, but will write this system in a technology database. And all the implementation tools and analysis tools will read write from this database to get required data to perform certain tasks like thermal analysis, power integrity, timing, DRCs, and not only on the single fabric, but on the whole system. So here you see the front end integrity system planner features. I don't want to go into too much detail, so it allows you to stack your different fabrics in the system. It will do interface alignment validation. So that's a topic that you need to ensure you can do system level verification, checking the connectivity, do system or LVS as well. And you can also use it for advanced bump and TSV planning and planning your interfaces. It even allows you to create the system netlist, so the connections between the different components in your system, and even allows you to optimize it. And important for these 3D designs is that you also need to have from time to time a 3D view to check how would this look like in 3D. So a 2D view like you typically have in PCB package and IC design is not sufficient. You want to see how this would look like finally in a physical 3D view. And the different tools provide these different 3D views. And also, as I mentioned, there is no one super tool that would address all the different technology aspects. So therefore, all the implementation tools, they have their own special ways or implemented routers. For silicon interposer, we have a specific routing engine providing also shielded routing, analog die routing or digital routing is from the style often different. And also in the RDL type, in Allegro Package Designer, we have different ways of addressing these routing challenges of high density interconnects like micro vias, buried vias, through-hole vias, and so on. And the beauty of this Integrity 3D cockpit or planner is that we provide also a kind of flow manager, so you don't need to import, export data between the different tools. The database is kept in this multi-technology environment, and the flow planner would guide you through the steps of designing this system by creating floor plan, doing the individual implementation task of the different dies, doing power integrity, thermal integrity, static timing, system LVS. So it's a single workflow you can go through and focus on the individual task an individual engineer would like to focus on. And this workflow manager will then access or start the individual point tool that would do the task or the analysis. We also have 3D this platform connected to the thermal analysis and power and SI/PI analysis, focusing now on the system, not on a single fabric. So doing also early thermal analysis, either with Celsius or with Voltus on the chip side, on the silicon side, or on the right side, also tools that can do power ripple, impedance of power nets, eye diagrams. So all the different SI/PI analysis are enabled in this flow. And also very important for these kind of stacked die and chiplet packages is warpage analysis. So with thermal analysis tools, we can also directly read in the stacked database into the analysis tools, and we can apply during the manufacturing stage, you will have the substrate, and you will have a temperature profile to solder the individual dies. You may have an interconnection, another die mold, and finally the molding. And so in the manufacturing process, you will apply to your package a certain temperature profile, and this will be simulated and will finally end up in a warpage analysis and color plots, and you can analyze if this is okay or if you need to modify something in the assembly process. And the same as for stress analysis, the tool can also calculate individual stress on very detail on the bumps, on the balls, on the individual dies, and will give you the stress figures. And as mentioned, it's very hard at the moment still to get the assembly design kits. We are working with a foundry to enable or ease this process. So if you want to do such a system, you need all the information about the technologies, the stack ups, the material information. You need to have libraries of the component. You need to know how what to respect regarding assembly, so the assembly rules. For the SI part, you may have interfaces like DDR, PCIe, so you need to check for the compliance of these interfaces. And then you have also manufacturing rules, both on the silicon and the whole system side, and also some rule decks the foundry will provide for these advanced packages where you need to check your manufacturing data against the foundry provided rule deck. So again, the tools and flows explode if you go into these multi-chip design phase. And in our view, EDA is fundamental for enabling such systems, and especially if you have a single vendor platform, that would ease also and the time to market, because you don't need to deal with exchanging data from one tool to a third-party tool. And Cadence invested a lot in system design since many years, so that's in our main strategy. We acquired recently also CFD type tools to simulate also full airplanes, boats, turbine machines, and so on. So from chip, package, board, onto system and data centers, we can provide tools and solutions to address these system designs.